This lesson is on binomial experiments where the probability of each event does not equal 1/2. Remember, with binomial experiments, you have to have two mutually exclusive outcomes. You need to have a fixed number of trials, and each trial must be independent of the other trials. Some examples of binomial experiments are when you have 5 children, how many of them are right-handed or left-handed? You have a team with an 80% chance of winning and they play 3 games. You flip a coin that has a 30% chance of landing on heads, and you would need to say how many times you flip the coin. Maybe you flip it 4 times. One of the easiest ways to work with this is to make a tree diagram. This is possible if you don't have a whole lot of different options for things to happen. Here we have a person has 10% chance of being left-handed. What is the probability that 2 kids out of 3 in the family are left-handed? Since we only have a total of 3 kids, making a tree diagram is not going to be too big. For the first child, your options are they could be left-handed or right-handed. The second child, after the first, could either be left-handed or right-handed. So you could get lefty-lefty, lefty-righty. Or you could get righty-lefty, righty-righty. That's for the first 2 kids. Then you add the third kid. That kid could also be left-handed or right-handed. So if we look at our tree diagram, we have left-handed, 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 left, 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 or we have left, left, right. We could do left, right, left, or we could have left, right, right. So just to be sure we understand, this would mean that the first child was left-handed and then the next 2 children were both right-handed. Then if we continue making our list, right, left, left, right, left, right, 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 right. You have a 10% chance of being left-handed. So the probability of each of these things is not equally likely. And we're looking for 2 of the kids to be left-handed. So if we want 2 kids to be left-handed, that could be this one, or this one, or this one. The probability that this first one happens is 0.1 times 0.1 times 0.9. Because the probability the first child is left-handed is 10%, the probability the second child is left-handed is 10%, and the probability that the third child is right-handed is 90%. 0.1 times 0.1 times 0.9 is going to be 0.009. The probability that it happens like this with the second child being right-handed is 0.1 for the left-handed, 0.9 for the right-handed, 0.1 for the left-handed. We multiply that, 0.009. Then for the last one, if you want the first child to be right-handed, that would be 0.9 times 0.1 times 0.1. They're all the same because all we did was multiply in different orders. Now what we want to know is the probability that this happens, or this happens, or this happens. And we know when we're looking for this, or this, or this, we add them together. So we get 0.027 is the probability that a person has 2 kids out of 3 being left-handed. It's not a very big chance. When you see that we're adding the same number over and over, we know that we could also use multiplication to do that. We could have done 0.009 times 3 because there are 3 ways that this could happen. So if you find the probability it happens one way, you can multiply it times the number of different ways it could happen and still end up in the same place without having to do quite so much work. That's helpful when you don't have a tree diagram and you don't have this list of all the different outcomes. In this problem, we have that a vaccine has an 85% success rate. If 5 kids in a family all receive the vaccine, and then all of them are exposed to the disease, what is the probability that 2 will contract the disease? Well, if that happens, for 2 of the kids, the vaccine fails. For 3 of the kids, it's successful. A tree diagram for this would be pretty tedious, but you could do it. But we're going to do it a slightly simpler way. We have 5 kids, we have 2 vaccines that failed and 3 that were successes. So the probability that it happens just like this, there's a 15% failure rate, so 0.15 times 0.15, and then an 85% chance success rate, so the chance that these 3 vaccines work is 0.85. This, when we multiply it together, is going to give us the probability that it happens exactly this way. When we multiply this together, we get 0.0138, and I'm just going to stop it right there. Now, this is only the probability that happens just like this. We could try to figure out how many different ways they could be ordered by just making a list, or we could do it the same way we do when we are ordering the letters of a word when we have repeated letters. We've done an example like that with the word bananas. How many ways can you order the word bananas? And the way we do that is to say how many letters we have. We have 5 letters, so that's 5 factorial, over, we have 2 F's, so 2 factorial, and 3 S's, 3 factorial. So 5 times 4 times 3 factorial over 2 times 1 times 3 factorial. You get 20 divided by 2 is 10. That means there's 10 different ways these letters can be ordered. So we would have this number 10 times. So we're going to multiply it times 10, 0.138. So there's about a 13.8% chance that this could happen. Okay. The steps for finding the probability of a binomial experiment when the probability doesn't equal 1 is to first write down one possible favorable outcome. We did that when we said 2 failures and 3 successes. Then find the probability that this specific outcome happens. We did that when we multiplied 1500ths times itself twice, and then 8500ths times 8500ths times 8500ths. That gave us the probability that this specific outcome could happen. Then we found the number of possible ways the favorable outcome could occur. That was when we did 5 factorial over 2 factorial times 3 factorial and got 10. And then the last step was to multiply the probability that we got in step 2 times the number of ways it could happen in step 3, and that gives you your final answer.